Let's talk about mastering arrow pushing in organic chemistry. Now, being able to use arrows to indicate the movement of electrons is extremely, extremely important in organic chemistry. It's the way you're able to do synthesis, right? Retrosynthesis. So if you know how to use arrows to show the movement of electrons, you can be given A plus B to give you C, right? Let's say you had no idea what C was. You can literally write a reaction mechanism between A and B and figure out what C is. So when I say it's important, it is extremely, 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 extremely important, right? It's your Bible to reaction mechanisms. And being able to write reaction mechanism is how you can figure out a product. It's how you can be given a product and figure out the starting materials. It is extremely important. It's how you become a master in the sense that they could throw any starting materials at you and you can figure out the product because you know how to use arrows. So let's talk about the rules and what is allowed when you use arrows to show the movement of electrons. So notice what I'm saying. We're using the arrows to show movement of electron. Extremely important in reaction mechanism. Um, and just writing chemical reactions, right? So the first rule is let's just talk about what the arrows look like. So you have a double-headed arrow, and if you draw a double-headed arrow, it is showing the movement of two electrons, right? And this right here is the tail or the end of the arrow, and this is the head, right? You also can have a single-headed arrow. Your single-headed arrow, of course, shows the movement one of one electron. All right. When you draw, next rule, when you draw your arrow, right, your arrow never directly show the movement of an atom. Always remember that. When you draw your arrow, it does not directly show the movement of atoms. Your atoms move indirectly because of a broken covalent bond. So, for example, let's look at something. Let's pretend that this is a base. We have a lone pair plus some type of acid, right? So, and this is the next thing I'm going to tell you. You generally draw your arrow. So, the end of your arrow or the tail goes from the source, which is what's rich in electron, towards your sink, which clearly exactly what it says sink. It's an area or an atom or ion or molecule that lacks electrons, right? So it's hungry for electrons. So from your source to your sink, right? So this arrow here means these lone pair here make a bond with this hydrogen. I'm going to talk a lot more about this when we look at the pattern for mechanistic pattern that you need to look for in organic. So it would be B, H, right? A. But we know that can't happen, right? Hydrogen cannot have two bonds, two bonds on it, right? I'm trying to do the rules one by one. So in order for us to have hydrogen not have two bonds, you move the two electrons, because remember, two electrons constitute this bond. So this arrow means the two electrons in this bond go onto A to give you A, and I gave it two electrons, so now it's A minus, right? So let me just do rule two. Rule three and four is tying into two a little bit. But trying to show you here that atoms, when you write reaction mechanism and the flow of arrows, your atoms do not move directly, right? So you couldn't have drawn, okay, whoop-de-doo, put um let's put the hydrogen with the Br. Let's just draw hydrogen goes to the B. Sorry, you can't do that because that's not what's happening. So the hydrogen moved indirectly toward to B, right? Because you broke the bond between hydrogen and A, right? Because hydrogen can't have two bonds. So you need to remember that. The arrows do not indicate the movement of the atom. The atom move because this bond was broken, which takes me to rule number 3, right? In rule 3, you must draw your arrow from your source to your sink. So the arrow starts at the source, right? And it ends at the sink. Your source is generally a lone pair or a pi bond. Because your source, it's exactly what the word means in English, is rich. It's rich in electrons, right? So your electron source is usually a lone pair or a pi bond. Your electron sink, which is where the head of the arrow ends, is generally an atom or a molecule or an ion, right? That can accept a new bond or a lone pair of electrons. And then there is rule number 4, which I highlighted here. Um, Always remember this. Bond breaking will occur to avoid overfilling of valence, right? On an atom serving as your electron sink, right? So here, like I said, this is making a bond with the hydrogen. Hydrogen cannot overfill its valence. So you have to break the bond between hydrogen and and A, right? So hydrogen will go with this. It's almost like it's stealing it, right? I have the lone pair here. I'm going to take hydrogen, but in order for me to take or steal the hydrogen, it is already bonded to A, so I have to break them up, right? In order for me to steal the hydrogen, I have to break up the bond between H and A. To break that bond, you literally draw an arrow. This arrow just means the two electrons that constitute this bond go onto A as a lone pair. It clearly couldn't go onto A like this. That doesn't even make any sense. So when you put, and these are the little things you have to put in your brain, right? When you draw a bond when you draw an arrow from a bond onto an atom, the electrons in the bond become a lone pair. You can't just out here as a bond sticking out, right? It's not a minus charge, it's a bond. The bond can't be sticking out by itself. It's got to be bonded to something. So the two electrons here will go into A as a lone pair. When you draw a lone pair towards an atom, it now makes a bond with it, right? So it's now sharing. Okay. When you watch the video with the 4 mechanistic patterns, I will go more into detail about one, how this no longer has a minus charge, why this now has a minus charge. But always remember, in order for you to not overfill your valence when you write a reaction mechanism, you have to break the bond. Okay. Now, it's okay if you're writing a reaction mechanism, it is okay for your atoms to have an underfilled valence. So for example, and you'll see this when you watch the video on your 4 mechanistic patterns, you can have this when you write a reaction mechanism. It's called a carbocation. So this is an underfilled valence because remember, your carbon needs to have 8 valence, those 8 valence electrons and the 4 bonds. It doesn't have 4 bonds here. It only has 3. So you in a reaction mechanism, don't forget you can have an underfill valence, but you cannot overfill a valence. So these are the 4 rules. You can watch my next video. I'm going to go through the 4 mechanistic patterns that you will encounter in organic, a little bit more step by step what the arrows mean in terms of lone pair, and if it goes to atom, what happens, etc.